Now we'll solve the problem on principal stress, and here I'll show only a single questions of the principal stress, and in the single questions number of possibilities of the questions I have included, so that if you solve this question, the single question itself, you will be able to solve any problem of the principal stress. So this is the question. The state of stress at a point in the material is as shown in figure. Determine first principal stress and its plane. Second, maximum shear stress on tau max plane. Third, normal stress on tau max plane. Fourth, the resultant stress on a 20-degree plane with the axis of 400 megapascal stress. Fifth one, the resultant stress on a 70-degree plane with the plane of 400 megapascal. So these are the possibilities of the question which I have included in a single question, and this is the figure of this question. This is the machine component, and here in this x plane, the sigma x and tau xy stress component acts. So the sigma x value is 400 megapascal, tau x value is 100 megapascal. Similarly in y plane, so 200 megapascal sigma y, and the tau yx is 100 megapascal. The tau xy and tau yx both will be the same value in magnitude wise. So here you can see that if you solve the problem as per our sign convention, we have to think only two very important part to solve this problem, this principal stress problem. First, to select the reference plane, and the second one is the sign convention. So after selecting this, you can solve the problem. So first, as per our sign convention, this is our sign convention that we can take. So here the sign convention is what we are taking. The sign convention, we are taking the sign convention for the tensile positive, compressive negative. If the shear stress rotates the body clockwise, we consider positive, and if it rotates anti-clockwise to the body or to the system, we consider negative. So this is our sign convention, and based on the sign convention we can take the value from this machine component or this complex state condition. This is the case of the complex stress state condition. So here the sigma x, which is 400 megapascal, is tensile in nature. That's why we will take the value 400 megapascal here, and the sigma y, which is compressive in nature. So because as per our sign convention, compressive in nature, we will take the negative sign. So sigma y will be minus 200 megapascal. Tau xy, so tau xy we will take always from the reference plane. So the selection of reference plane is very important. Now the reference plane we select wherever the normal stress value will be more. So the magnitude of the normal stress will be more. That plane we will consider as a reference plane. So here you can see that this sigma x is a 400 megapascal and sigma y is a 200 megapascal. So sigma x is greater than the sigma y. That's why we will take this plane, this x plane, as a reference plane. So this will be the reference plane for us, and as per this reference plane we will take the sign convention of the tau xy. So tau xy, here you can see the tau xy, this shear stress tries to rotate the system anti-clockwise. So anti-clockwise we are taking here negative. So this value of the tau xy will be minus 100 megapascal. Because of the anti-clockwise we will take the negative sign. So one by one we'll solve the problem. As we have selected the reference plane and sign convention. As per the sign convention we have taken all the value here. Now one by one we'll solve the problem. So here the first question is principal stress and its plane. How to solve the principal stress and its plane? Now we can see the first is principal stress and its plane. To find out the principal stress, that is a sigma 1 and sigma 2, this sigma 1 is called major principal stress. This is the major principal stress, and the formula for this major principal stress is sigma x plus sigma y by 2 plus root under sigma x minus sigma y by 2 whole square plus tau xy square. So this is the formula for the major principal stress, and similarly the minor principal stress we can write negative now we can put the value here, and we will be able to find out the sigma 1 major principal stress and minor principal stress value. So sigma 1 is a major principal stress, and here we can put the value sigma x 400 plus sigma y, since it is a compressive nature, so we will take the minus 200 by 2 plus 400 minus 200 by 2 whole square plus minus 100. So value of this tau xy is minus 100 because anti-clockwise direction of the shear stress. So if you solve this problem, after the solving you will be get this will be the 100 plus, if you solve through the calculator, we'll solve here. So it will be 316.2. so total will be 416.2 megapascal. So sigma 1 will be 400 is positive, so tensile in nature. Sigma 1 is tensile in nature. Sigma 2, if you solve the minor principal stress, similarly you can put the value 400 minus 200 by 2, negative sign we have to take here only. Directly you can also solve the problem. So the sigma 2 will be minus 216 megapascal. If you solve, you will get this minus. So this is compressive in nature. Compressive in nature means compressive downward side, and this is tensile in nature. So here you can see the how we can solve this principal stress. This first question, for the principal stress we find out the sigma 1 value and sigma 2 value. So sigma 1 is a 416.2 megapascal and sigma 2 is a minus 216 megapascal. So this is the principal stress. Now the another question asking and the principal stress and its plane we have to find. Now next is to find out the principal plane. So principal plane. To find out the principal plane, we have the formula of this principal plane, that is 2 tan, that is tan 2 alpha equal to 2 tau xy sigma x minus sigma y. So if you put the value here, we'll get this principal plane alpha 2 into minus 100 divided by 400 minus 200. So tan 2 alpha will be, calculate, this will be minus 1/3. So 2 alpha will be tan inverse third. So alpha will be nothing but this minus 9.21 degree. So this minus 9.21 degree, this minus sign shows that this is the anti-clockwise direction. The sense of this alpha is anti-clockwise direction with vertical. So if you draw here machine element, so the anti-clockwise direction in this sense. So this is the vertical. With vertical, the alpha will be here in this anti-clockwise direction. Alpha is nothing but 9.21. So this is the plane called the principal plane. I'm writing here, this is called the principal plane. So principal plane is a plane which is at a certain angle alpha with this vertical. So this is called the principal plane. So alpha is nothing but here it is the angle of major principal plane, major principal plane, where the major shear stress acts. So here the major shear stress acts sigma 1, and the alpha 1 is called the angle of minor principal plane, which is nothing but alpha plus 90 degree. So here, since alpha having anti-clockwise sense, so if I calculate 9.21 plus 90 degree, so if you calculate, it will be 99.21 degree. Since it is anti-clockwise sense here, so it will be the anti-clockwise with alpha, that we can write here. So here in this diagram it will be 90 degree from this alpha, which is the anti-clockwise sense, where the sigma 2 will act. This is called the plane where the minor principal stress acts, since the sigma 2 value is negative, that is minus 216 megapascal, hence it is compressive in nature. So this is the plane, this is called the principal plane, where the major principal stress act, and this is called the plane where the minor principal stress acts. So here if I draw this element will be looks like this for this principal plane. Now the next question here, you can see the next question is the second one. Determine the maximum shear stress on tau max plane. So maximum shear stress, if you calculate, so maximum shear stress maximum shear stress as we know, the formula for this maximum shear stress on tau max plane, the second one. So here the formula for this tau max is this one, sigma 1 minus sigma 2 by 2. If you put the value of sigma 1, you will get megapascal, 316.1 megapascal. This is nothing but the tau max. And if you know or find out the maximum shear plane, that is nothing but beta 1, as we have discussed earlier in the formula section of the principal stress, that is nothing but alpha plus 45 degree. Since alpha is here the anti-clockwise direction, alpha is the magnitude is same 9.21 plus 45 degree, but since it is anti-clockwise direction, so the sense will be same minus 54.21 degree. So this is nothing but the anti-clockwise movement. So beta 1 will be the anti-clockwise with this alpha, and beta 2 will be nothing but beta 1 plus 90 degree. So beta 1 plus 90 degree, so beta 1 we know that this is minus 54.21. okay, so here directly we can write this 144.21. Since it is negative anti-clockwise direction, so this will be minus 144.21, and this is the anti-clockwise movement. This is formula for the beta 2, this is formula for the beta 1, and here since all values negative 9.21 because the sense is anti-clockwise direction, so the beta 1 movement will be anti-clockwise in this element. So here if we draw the element, and this is the alpha which is anti-clockwise direction with this vertical, and from this it is 45 degree, this plane of maximum shear, this is 45 degree, this is called the plane of maximum shear. Here I can write this is nothing but the plane of maximum shear. This is the plane of maximum shear where maximum shear stress acts. So from here if I draw the 90 degree from this, this is also called the plane of maximum shear where the maximum shear stress act. This the beta 2. So here the beta 1, this is the beta 1 and this is the beta 2 plane. So beta 2 plane, this would be the beta 2 plane, this would be the beta 1 plane. So if I make this element, this looks like this, which having a anti-clockwise sense in this diagram because the value is showing the anti-clockwise direction. So where in this plane the tau max acts, everywhere the tau max acts. Since we are taking, as per our sign conventions, anti-clockwise we are taking negative, so that's why the sense will be negative here. So this is the maximum shear stress on a tau max plane and maximum shear plane. We can draw in this way. Tau max plane. So normal stress on tau max plane. We know the formula of the normal stress on tau max plane is nothing but sigma prime equal to sigma 1 plus sigma 2 by 2, and that is nothing but the 416.2 plus minus 216 by 2. If you solve through the calculator, the 416.2 plus minus 216 is nothing but the 100.1 megapascal. So this is the normal stress. This sigma 1 is called the normal stress. Here we are denoting from the sigma prime. This is nothing but the normal stress on tau max plane. So normal stress on tau max plane. And the fourth question is the resultant stress on a 20-degree plane with the axis of 400 megapascal stress. Means we have to find out the resultant stress on a 20-degree plane with the axis of 400 megapascal. Remember it. I'll solve fourth one. So the resultant stress on a 20-degree plane, on a 20-degree plane with the axis of, this is very important, with the axis of 400 megapascal stress. Means wherever the 400 megapascal stress acts, from that plane we have to take the axis, and from that axis 20 degree we have to take. Means if we draw this machine component where the 400 megapascal act on x plane in x direction, so this is the 400 megapascal, here also 400 megapascal is there. So what is the asking in a question? The resultant stress, means that resultant stress we have to find out on the oblique plane. This 20 degree is nothing but an oblique plane. So how can we find out the resultant on the oblique plane? So we have a formula, this sigma r theta. Theta at particular angle, means resultant we have to find out at a particular angle, that is nothing but a 20 degree axis. So this resultant, to find out the resultant, we know the formula, that is sigma theta and tau theta on oblique plane. So in any oblique plane we have to find out the normal stress and the shear stress at a particular angle. So this is the formula for the oblique plane. Now the question is asking, find out the resultant stress on a 20 degree plane with the axis of 400. Now with the axis of 400 megapascal, so this is the 400 megapascal and we have to draw the axis from this 400 megapascal. This is the axis of the 400 megapascal. Now it is saying the resultant stress we have to find out on a 20 degree plane with this axis. So I draw the 20 degree plane. Okay, so this is the 20 degree plane from this axis, or this also write a 20 degree plane. Now we know that this is our reference plane. We have to find out the oblique plane always from our reference plane. So this is the reference plane, and from the reference plane how much degree it tilts. So if the any plane is there which is 20 degree from this axis, how much angle it makes from the reference plane, that is primary thing to find out first. Now how to find out? I draw this, just I shift this vertical plane here, just I shift here, or this vertical plane I shift like this. So now if it is 20 degree, this will be 90 degree, this will be the 90 degree, so this will be 70 degree for us. Again I draw to better understand here in a large view. If it is the 400 megapascal, and from the 400 megapascal, if it is the axis where the 20 degree megapascal, a 20 degree angle is making here, the 20 degree angle from this axis. So our primary aim to find out the angle or the plane from the reference plane, how much angle it tilts. So this is the our reference plane. So we shift this reference plane here because it's parallel, so I can shift here. If it is 20 degree, this is the 90 degree, so this will be 70 degree. Now here you can see that from this reference plane, this vertical reference plane, this plane which is in the 20 degree from the axis rotates here anti-clockwise 70 degree. So theta I'll take minus 70 degree. So now the theta value will be 70 degree, and because of the rotation anti-clockwise I can take minus 70 degree. So here the sigma theta we have to find out first, sigma theta. So sigma theta formula we know that this is the sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. So this is the formula for the sigma theta. Now if you find out the sigma theta, you have to put the value. The sigma x is 400 minus 200 by 2 plus 400 minus of 200 by 2 cos 2 into theta here is a minus 70 degree minus 100. So sine 2 theta is minus 70 degree. Now if you solve this, you will get, after solving, so this will be 100 and this will be minus plus minus 229.8 plus minus plus 64.27. So sigma theta will be minus 65.52 megapascal. Now we have found out the sigma theta value. So sigma theta value is minus 65.52 megapascal. Now tau theta, you have to find out the tau theta, and tau theta is nothing but the minus sigma x sigma y by 2 sine 2 theta plus tau xy cos 2 theta. If you put the value of all sigma x sigma y, theta and tau xy, you will be able to solve this tau theta. And tau theta, directly I am writing the value, it's 269.43 megapascal. So this is the value of tau theta. Now the question is asking, we have to find out the resultant stress at 20 degree plane. So resultant stress is nothing but the sigma theta square plus tau theta square. So sigma theta value is minus 65.52 whole square plus 269.43 whole square. So this is the resultant of this, and if you calculate the resultant of this, you will be able to find out the value 277.2 megapascal. So this is the resultant of the 20 degree plane from the axis of 400 megapascal. Now the fifth question is the resultant stress on a 70 degree plane with the plane of 400 megapascal. So the resultant stress on a 70 degree plane with the plane of 400 megapascal means the fifth one is we have to find out the resultant stress on a 70 degree plane with the plane of 400 megapascal. Means this is the machine component where the complex load are acting. So this is the 400 megapascal force is acting in this plane. So now the question is saying the resultant stress on a 70 degree plane with the plane of this 400. So this is the plane of 400 megapascal, and the resultant stress we have to find out on the 70 degree plane from this vertical plane. So this is the 70 degree. So this is the 70 degree. So at this particular plane we have to find out the resultant at this particular plane. Now again we have to use, because this is oblique plane, again we have to use the same formula of the sigma theta and tau theta. So you can put directly the value of the sigma theta. We know the formula, so directly if you put the value, this is the 400 here plus minus 200 by 2 plus 400, which is the formula. Okay, so 400 minus 200 by 2 cos 2. Since here we can say that this 70 degree oblique plane is rotating from this vertical plane. Here you can see the clockwise direction, so here theta will take the 70 degree positive. So 70 degree here plus minus 100 plus minus 100 tau xy into sine 2 theta. Sine 2 theta directly I am taking this 140 degree. Okay, so directly I am taking. So now here I am writing the sigma theta. So sigma theta value will be, if you calculate, it would be minus 194.8 megapascal. So this is the sigma theta value, and you can find out the tau theta value. If you find out the tau theta value, it will be the minus 116.225. Directly you can put in the formula, you can find out the tau theta value. Now you have to find out the normal, the resultant. So sigma r theta, theta means at 70 degree. So this will be sigma theta square plus tau theta square. You can put the value here, minus 194.8 square plus minus 116.225 square. Then the sigma r theta will be, you can calculate